Hi everyone, my name is Wang Shu. Today I would like to introduce you a fluid floating in the porous media. But before we dive into the mechanism of the fluid floating in the porous media, it's really important to understand why it's the porous media. Typically, the porous media is a material that contains a huge amount of the internal pores throughout the structure. And thanks to this unique structure, the porous media has been extensively used in the industrial or scientific field. An easy example that we can observe in our daily life is a sponge in the kitchen or the soil ground in a rainy day, and the rain will be absorbed into the soil ground since the soil ground can be seen as a porous media. The next, I will like to briefly talk some application in the porous media. The first one is the membrane separation. Because we know that the membrane can be fabricated with the polymer, and by deciding the pores of the polymer or the structure, we can separate some salt or the dye for the nanofiltration in the nanofiltration and the ultrafiltration. And next is I would like to mention is the air purification using the porous media. And by modifying the oil porous media with some certain electrical charge, some gas molecule with the same electrical charge will be repulsed, but the opposite will be captured into the porous media. Therefore, some toxin and matter can be captured using the porous media. And next is the characterization of the porous media. How to characterize our porous media plays a really important role in understanding of the mechanism of a fluid floating in the porous media. And there are two terms that can characterize our porous media. The first one is the specific surface, which is equal to total interface area, the area that is exposed to the fluid phase or the gas phase, over the total volume. And the second one is the porosity. Porosity is equal to the wall volume over the total volume. The wall volume here is only consider the volume of the penetrable volume. And we will get into the detail in the next slide. In real life, when we are fabricating our porous media, it's really hard to make sure all the pores have the connection to let the fluid go in or go out. So the porosity can be divided into three categories. The first one is penetrable pores, which means this kind of the pores have a connection to outside and or to let the fluid go inside. The next one is passing pores, which there is only an entry in these pores, but don't have any exit. And the third one is non-passing pores, simply just a hole, don't have any connection to let the fluid go in and go out. And next, I would like to talk about the tortuosity. And with the picture on the left hand side, if we take a square of the area as an example and zoom in, we can see the porosity, the structure of the porosity. And the tortuosity in the formula, tortuosity can be expressed the L mean divided by the L square. The L mean here is the real path of the fluid is the real path for the fluid, and the L is the shortest path from the one side to the other side. Intuitively, the short path will be a straight line.
Hi, my name is Tian, and I will continue from where Wang Zhenxiu left off. A porous media is a material with internal pore structures that can either be empty or filled with liquid. In this presentation, I will focus on the available volume fraction, REV, partition coefficient, and permeability. Let's start with the available volume fraction, or KAV. This describes the fraction of the total volume that is accessible to a specific solid. The formula highlights the relationship between the available volume and the total volume. Uh, its volume is always less than the porosity, as some Wally space may be too small or inaccessible due to molecular interaction. Influencing factor including pore size distribution and interaction of solid molecular with solid surface. Next part is REV. REV is the smallest volume that essentially represents the properties of an interporous medium. It must be large enough to average out variation in pore size, but small enough to define local physical quantities, like porosity. For example, in biological tissue, pores can vary significantly in size, but an RUV allows us to simplify and analyze the medium uniformly. Uh, the formula for porosity shown here represents the ratio of water volume to the total volume. Also, RUV is widely used in groundwater analysis, biological tissue, and material science. Now, let's look at the partition coefficient. This measures how solute distribute between the void space in the porous media and the external solution. The formula relates the available volume fraction and the porosity. Swimming factor influence the partition coefficient are the size of the solute compared to pore size, uh, electrostatic interaction between the solute and the solid surface, and the connectivity of the pores. The solutes can be excluded from certain pores if they are too large. Next, let's discuss permeability, which quantify how easily a fluid can flow through a porous medium. Density's law mathematically describes this relationship. The, the fluid velocity is proportional to the pressure, which is a constant. Um, for the application of permeability, um, from understanding groundwater movement to oil and gas recovery, and even analyzing tissue fluid dynamic in biological system.
Hello everyone, this is part 3 talking by Qi Lu. Today I'm here to share with you about Darcy's law. In fact, it's an important law in the field of hydrogeology. Darcy's law not only provides valuable theoretic support for understanding groundwater flow, oil extraction, and environmental engineering, but also lays the foundation of our practical application and technology development in chemical engineering, like our today's topic, flow in porous media. In the following talk, I will discuss the origin of Darcy's law, its derivation process, and its application. Through this journey, I hope to help you better understand this basic principle. Okay, next, let's give you a briefly introduction of Darcy's law. In our chemical engineering field, Darcy's law is an equation that describes the flow of the fluid through a porous medium and through a Helen shell cell. It was first formulated by Helen Darcy in 1856 based on experimental data from flow through a sand flatter. Darcy discovered that the flow rate is proportional to pressure gradient, and the general form of this equation is showing under there. Well, Darcy's law is a fundamental tool for describing flow through porous media. It is not using under all conditions. It has several limitations. They are shown in this slide. First, the flow must be steady state, and second, the fluids are incompressive. And then for non-Newtonian fluid and Newtonian liquid at high velocity, and for gases at very low and very high velocities. Also, flow should depend only on pressure gradient and is independent of the velocity and directions. Finally, the porous medium are homogeneous. Okay, after talking about limitations, we should use them for derivation of Darcy's law. Okay, firstly, let's start derive the Darcy's law with the Navier-Stokes equation. First step, the Navier-Stokes equation describes the motion of fluid and is given by this form. And rho is the fluid density, and v is represent velocity, p is pressure, and mu is viscosity, and F represents the body force like gravity. Then, for a steady state flow in a porous media, we assume first this is no time dependence, so we get dv over dt equals 0, and the flow is driven by a pressure difference, and the body force like gravity can be dropped, so we can get F equals 0. So let's do the step 2, assume for flow through a porous media. Because of the elimination of this Darcy's law, we should simplify the Navier-Stokes equation. Firstly, this flow is incompressive flow, so we got this, and we assume there are a laminar flow, so we can represent it as this, and we can drop this form. And because of this simplified, we get the step 3. This is the final simplified equation of Navier-Stokes equations. And in this case, the pressure gradient is driven by the force, and the velocity field only has a component along the x direction. So we only see the one dimension on the x direction. So we get this form, and we integrate it twice, so we get this one. In many cases, we should simplify this form, this integrate form. In many cases, this dp dx is a constant, so we only can use this dp dx represent this one. And we have the boundary condition, so we get this. As what you see in step 3, we get the relationship between velocity and pressure. So in the next step 4, we will find the equation related to the flow rate Q. The flow rate Q through a cross-sectional area A is given by this equation. Now for the steady flow through a cylindrical porous media with constant permeability, the pressure gradient can be approximated into this form. So we can simplify our equation from this into this. Finally, we should integrate over the length of the column from 0 to L. We obtain the total flow rate in this. And inside this equation, K is the probability of this porous media, which is determined by the media's porosity. So these 4 steps will arrive at the final form of this Darcy's law. In summary, Darcy's law is a simplified model that describes the flow of fluid through porous media. It can be derived from the Navier-Stokes equations. The flow rate depends on the pressure gradient, the permeability of the medium, the viscosity of the fluid, and the geometry of the fluid path.
And here, we're gonna talk about some examples of the application of Darcy's law in engineering. And here, we first will talk about we use Darcy's law to predict oil productivity because in the reservoir underground, it is mainly steady state flow and of course it's porous medium. So the Darcy's law can be used to calculate, or in other words, it can be used to predict oil productivity. And from Darcy's law, we can know that QR equals AR times K over mu BO times dPdr. And here, AR means the radial area of the flow through the well. In other words, it's the inner surface of the well. So the inner surface of the well is 2 pi r HR. And here we use HR to describe the total length of the well. And K is a permeability. Mu is the viscosity of the fluid. Here the fluid is oil. So easily the mu is the viscosity of the oil. The BO is oil formation volume factor. And then we incorporate equation 2 into equation 1. Then we get QR times 1 over RDR equals 2 pi KH HR over mu BO dP. Here, we use KH to describe permeability. It means horizontal permeability instead of permeability only. And then, because the reservoir energy may drain oil from the side or the bottom of the well. If the edge water or bottom water aquifer occurs. So we integral R from RW to RE. It means from the well to the external drainage of the reservoir. And we integral P from PW to PR. It means from the falling well pressure to the reservoir pressure, which is PR. And then after some easy algebra, we get QR times log RE minus log RW equals 2 pi KHHR over mu OBO delta P. And here, delta P means the pressure drawn down. And then what we want is to predict oil productivity. So we had to know how to calculate it. And then equation 6 gave us the formation of the productivity index. Tells us Q equals JW, which is productivity index, PI, times PR minus PWF. And then we got PI equals Q over PR minus PWF. And here, PWF means pressure of the falling wheel. And now, from equation 5, we get Q. And from the same equation, we get delta P. And here, we can calculate the PI, or in other words, JW. And then we substitute the Q and PR minus PWF into equation 7. Then we get equation 8, which is the JW. And here, because of there's some difference between calculation and real world, so we use ISG to fix the equation. It is the geometric gain factor. It respect it represents the additional pressure loss caused by fluid convergence. And then finally, we use Darcy's law to get oil productivity index.